So, hello everyone. This is lecture 17th. In the last lecture, that was 16, we studied about the acoustical and the optical branch. Means we didn't studied actually. We just solved the diatomic crystal equation, okay, diatomic vibration equation. And we found these two equations for the frequency of vibration. And we call the just them, we gave them the name optical branch and acoustical branch. Means we just name them, we don't know that what is the actual physical meaning of this. Okay, so well, in the today lecture we're going to study that part. Means we will know what is these equations and what they refer in physics. So let's first study this second one, the acoustical branch. Well, somewhere you are getting this idea that acoustic means the sound wave, so it is something related to that. So let's see. Let's first do some mathematics, some more mathematics. Let's take this equation. And now we have two, three cases as we did in the monoatomic lattice vibration. So first we take for the long wavelength reason. For the long wavelength reason means the k equal to 2 pi by lambda and k will tends to 0. K will tends to 0, k will very small. Then we know that when k is small, then sine k will be proportional or equal to k, approximately equal to k. So we just substitute the value in this second equation. We will get here it is k. So we'll get something like this equation: beta 1 by m plus 1 by m minus beta 1 by m plus 1 by m whole square minus 4k square a square divided by m capital M 1 by 2. Okay, you guys know what is small m and capital M. These are the masses of different molecules, sorry, different atoms in a particular cell. We have two atoms in a unit cell. That's why we are calling it diatomic unit cell. Okay. So okay, and k, you know that. So we all know what are these terms. Now let's move. And this a is nothing but the distance between the atoms. Okay. So if we just take this common, means take this term out, then according to the from under root we will get 1 by m plus 1 by m out, and we will take this whole term common, beta 1 by m plus 1 by m. Then we'll get 1 here, and it will be minus, and then it will be common, then it will give us m plus m, and we'll get something like this, the square term will came here from here. When we take this common, the m plus m square will come down, and square will give us on the numerator. So just it's just mathematics, you can solve this. Means take this common first, then take this beta 1 by m plus 1 by m common, then you will get something like this. Okay, this under root is on this. Now just take it inside. So minus 1 minus minus plus will get something like this, 1 1 will cancel out, and then now what we did here, we actually solved this equation by binomial expansion. Okay, means we can solve this. Okay, 1 by 2, it will give us 1 minus 2 by 1 m plus m square. So and the multiplication, we will get this equation. So this is just we solved by the binomial, you know that. From here 1 1 will cancel out, and then will cancel out and this give cancel out the square term, and we'll get something like this. This is just a normal mathematics, I hope you are getting. Beta 2 upon 1 plus m plus m, k square a square. Now the omega negative will be under root 2 beta by m plus m k. So we get the expression, means the dispersion relation for the long wavelength region, and this will be this. When k is equal to 0, the omega negative is equal to 0. It's not negative, it's just representing the acoustical branch. So omega negative will be 2 beta by m plus m ka, and it will be 0 for the long wavelength region. Okay, because k equal to 0 will give us 0. You can get this 0 from here directly also. means when k tends to 0, then just instead of putting sin k equal to k, just give sin k equal to 0. Then we will get 1 plus, this will give us beta, and root will cancel out this, so this whole term will cancel out this, it will get omega equal to 0. So you can get directly or from this way, both will give you the same result. Now the second case for the cutoff frequency. First it was for k equal to 0, means long wavelength region. Now we will take for the short wavelength region, and k will be a finite value, so we can't approximate sin k to k. Okay, so we need to solve this now. So cutoff frequency meaning the maximum frequency, so we need to maximize this equation. So how we can maximize this equation? Just see from here, if this term is minimum, then this difference will be maximum, and then this whole term is maximum, then we will get the minimum value of the whole term. So we need to maximize this to minimize this whole equation. So how we can maximize this? Just sin k should be plus minus 1, only then it can be maximized. So it can be 1 only when k equal to pi by 2 and k equal to plus minus pi by 2a. So that's how we can maximize, and the maximum value will give us 1 here, then 4 by mm. So equation can be written as this, in this form. Now just open this square, 1 by m square plus 1 by m square plus 2 by mm, then it will give us something like this and cancel out. Then it will form just a square plus b square minus 2ab form. Minus 4 will give us minus 2 here. So we'll get 1 plus 1 by m minus 1 by m ka whole square, and give us 1 by m minus 1 by m. Substitute this value inside, then we'll get something like this. Now beta by small m will cancel out beta by m here, and beta by m plus beta by m will give us 2 beta by capital M. So from here we get the frequency equal to root 2 beta by capital M. Root 2 beta by capital M. This is for a short wavelength region or a finite value of k, and this value we get at k equal to plus minus pi by 2a. So this is nothing but maximum frequency possible, and minimum frequency was possible at k equal to 0, that was 0. Okay, so if we represent this in a graphical form, then we will get something like this. Means just forget this upper side, it's for the optical, we will study it later. Just see this below this line, this graph, it is 0 at k equal to 0. This is for the acoustical branch, and at pi by 2a we are getting the maximum frequency, that is 2 beta by m. We just calculated from here, so we'll get something like this curve, and this curve is same as we have studied for the monoatomic vibration. Let me show you. This is just like this as we get from the for the monoatomic. Okay, so this is nothing but the acoustical branch, so it's like a sound wave, and that is acoustic, and we will get the same type of curve for any type of any means any atoms in a unit cell. We'll get the same result because it's sound wave and it transferring in the same way. Okay, so we'll get the same result, but now just let us study the optical branch, that is this equation, the upper one. So let's see. First is when k equal to 0 we have to study. K equal to 0 means the long wavelength region. That will give us what? That will give us. So here is the equation. When k will equal to 0, this will give us beta 1 by m plus 1 by m. This will give us 2 beta this. So the omega will be this frequency for the long wavelength region. This frequency you will get, and now we need to find the pi by 2a or minus pi by 2a. So this will give us 1, this will give us 1. So you can see that if this term now maximize, then this will be minimum and adding will be minimum. So this, if this will be minimum, then whole term will be minimized, means we will get the minimum frequency. So see, in the acoustical branch we will getting the maximum frequency at k equal to pi by 2a, but in the optical branch we are getting the minimum value for frequency in the optical branch. Okay, so we see that at k equal to 0 we get this frequency. At k equal to pi by 2a we will get here 4 by mm, and it will give us 1 by m minus 1 by m ka whole square. Then this will cancel out the term capital M, and we will get the this small term 2 beta by m. And you will see that this frequency is lower than this, less than this frequency is less than this. Okay, so now we can represent this frequencies also in the graph. At the pi by 2a we are getting the minimum frequency for optical branch, and that is actually greater than, or you can say this is just equal, means this we are getting here. Omega plus will be, yes. So for the acoustical branch it was capital M downside, so it will be small as compared to root 2 beta m, because here m is small. So we are just getting the higher value, some higher value here, but it is its minimum value for the optical branch, and maximum value is 2 beta 1 by m plus 1 by m, and it will be same here also, the 2 beta by small m. So we'll get this type of curve for the optical branch, and acoustical branch will get this type of curve. Just remember that for the long wavelength region, we are getting maximum frequency for the optical branch and minimum frequency for the acoustical branch, and that is nothing but 0. So I hope this is clear to you. Now let's just move forward towards understanding the actual physical meaning of these optical and acoustical branch. So now the mathematics is a little bit over, but it won't be over ever. There will be mathematics all over the physics because it's the language of physics. Now physics of optical and acoustical branch. For optical branch, first we will study for k equal to 0. Now we derived these equations, two equations for the diatomic lattice vibration, and we get this type of equation. Here a is nothing but amplitude of small m, and b is nothing but amplitude of capital M, and from here we get that matrix and determinant we calculated, and we get all the dispersion relation from these equations. So what we gonna do here now? Now we will see that for the long wavelength region, just see this equation and put k equal to 0 here. What we will get? We will get minus 2 beta, this will be 1, then minus 2 beta a, and here is not, so it will get this. Now we know that for k equal to 0, omega plus will be, we calculated this 2 beta 1 by m plus 1 by m for the optical branch. We are studying optical branch, okay, so that's why we taken the omega positive as this frequency. Now just substitute the values, and 2 beta minus m square of, not square, it is already squared, so we'll get this, and you will get 2 beta capital M by small m, then m will be cancel out, and you will get 2 beta, and 2 beta will cancel out. So just solving this, it's a basic mathematics, you will get this equation, a by b equal to minus m by m. Now what this represents actually, you see that a is the amplitude of small m, b is the amplitude of capital M. They are inversely proportional to the mass, their masses. Means obviously if m is smaller, then a will be higher, and if m is larger, then a will be smaller. Now what this negative sign represents here? Negative sign means when a or the one particle is moving this side, then the other particle should moving the opposite side, means they should be moving in the different direction, opposite directions. So that's why we will get then a by b equal to negative. Okay, so this shows that atoms of mass m and capital M are oscillating with opposite signs, with also a is inversely proportional to m, b is inversely proportional to capital M, and if it is represent the small m and capital M like this, then they are moving in the opposite directions. particular time when we observe them, they will be moving opposite to each other. This type of oscillations are produced when optical IR radiations incident on the crystal. So the physical meaning of optical branch is that how it is possible to produce such type of oscillations. Means they will be moving this and it will be moving in this direction. They will be moving in opposite direction. So how it is possible? So let me give you this example. Just consider this ionic crystal NaCl. Now we have the ions inside, the plus and minus, the Na plus and the Cl negative. So if we apply a electric field, an electric field is nothing but giving us the EM radiations. So we applied some EM radiations which will give us the electric field, very strong electric field. And you know that positive charge will move in the direction of electric field and negative charge moves in the opposite direction of electric field. So we just applied here, then you will see that it will moving from this side, it will moving from here, it will here, it will here. So it just the what we just observed here, it's just the same result we are getting. And just like we can show in the capacitor or such type of plates, then it will be oscillating in this way, means in the opposite directions. So that was the reason why we call it the optical branch, because here this type of vibrations can be possible in the crystal only by the optical IR radiations only. And it doesn't mean that only these ionic crystals can produce such type of vibrations, but simple neutral molecules can also produce, means they should be diatomic at least, just they should be diatomic in a, then this type of vibration can be produced. Like let me show you this type of vibrations. To induce optical vibration, it is not necessary to have ionic crystal, but even neutral crystal can induce such vibrations due to polarization. The only requirement that crystal be a diatomic crystal, two atoms per unit cell. So it can be produced by polarization. So what is polarization? Well, I already told you in the lecture, but let me tell you again. Just like we have some neutral structures, crystal structures like diamond, magnesium, zinc, etc. So just consider this. Means two carbons are here. When you apply the electric field, then polarization will take place. Means the electron cloud will shift. The electron cloud will shift in the opposite direction of electric field. So you will see something like this. This is nothing but charge probability. So this electron cloud will shift in this direction. So the molecule will be ionized, and we will get something this way, means negative and positive. Now when we have this type of system, then it will definitely oscillate in the opposite direction when we apply the electromagnetic radiation or the IR radiations. So we are getting the same results as the ionic crystal. So it is possible to produce this type of vibration in ionic crystal. Now what is in acoustical branch? We just studied the meaning of optical branch. Now let's see the acoustical branch. When k equal to 0, when k equal to 0, just try to solve this equation, the second one. And what you will get when k equal to 0 for the acoustical branch, omega is 0. Omega is 0. Then you just solve this. This will give us 1. Then a by b you will find equal to 1. You will find this equation, a by b equal to plus 1. Means the amplitude will be same for both masses in the acoustical branch, and it is plus sign, means all will be moving in the same direction, all will be moving in the same direction. So this is the physical meaning, means acoustical branch is nothing but the sound wave branch, or the sound wave we can observe in it. So it is like what happens in the sound wave, it's just rarefaction and the compression. So when we speak something or we applied some force like in the air molecules and their disturbance, if they are moving in this direction, then they will feel some compression, and if they are moving in this direction, they will feel the rarefaction. So that's how, and all will be moving in the same direction. So this is acoustical branch. Acoustical branch can be produced when sound wave, acoustic wave is incident on the crystal. Means this type of vibration will be produced inside a crystal only when the sound wave type or the acoustical wave is applied. Okay, they will be incident then we will have the rarefaction compression inside the crystal, and this will be this way, means all will be moving in same direction, either in this direction or in this direction. So I already told you, if they are moving in this direction, then the wave will cause the compression, and they are moving in this direction, then they will feel the rarefaction. Now it's over for today. We understand the meanings and there's some mathematics. So I have some homework for you. Try to solve these questions. Then tomorrow we will discuss in the next lecture, the 18th one. And just try to first solve by yourself, because this will improve your ability of reasoning and solving problems. Otherwise, I will just tell you, then you will lose the opportunity to learn. So just try. First, prove that at k equal to plus minus pi by 2, atoms of mass small m is at rest in the acoustical branch. And second is, atoms of mass capital M will be at rest in the optical branch. Second question, discuss the behavior of acoustical and optical branch when m is decreasing, when m equal to 0, when capital M is increasing, or when capital M equal to 0. Also, comment on the Forbidden gap due to change. Okay, means just see this. Okay, change in M and capital M. Means when we found this graph, then we found some gap between these frequencies. So these frequencies are nothing but the forbidden gap, means the frequency which can't be achieved inside a crystal. So you need to comment on the forbidden gap due to change in the small m and capital M, and see the effect of these factors on the acoustical and optical branch. Just try to solve them. Tomorrow I will discuss. Then we will move forward to the modes of vibrations in the acoustic and optical branch. So okay, thank you, it's all for today.